So, yeah, let's get started right away because I just want to finish covering the material left over from the last class. So, what we had done is we wanted to synthesize not just data, right? Not just natural numbers or lists which satisfy a constraint. I want to synthesize programs. So, in order to do that, we implemented a relational version of an evaluator for a very simple language which contains constants, a single variable, and this plus expression, right? And immediately what you can do is you can execute programs um, using the auto tactic. So the way to read this is there is a variable var, right? That's a natural number. That's the assignment for the construct var whenever it appears, right? So this is the actual value that's a natural number. So the what this example says is that if you evaluate this expression, which is plus var plus right 8 plus var, where whenever you see a var, you use the natural number var. That would be the same as the natural number that is obtained by var plus 8 plus var, right? If you see, I mean, it seems a bit silly, right? So this one is exactly isomorphic to this one. And what's the point? There is a point here because this is a natural number, right? And what we are writing here is actually a natural number result. And we are relating the evaluation of this program essentially to the result here for every possible variable assignment for this var. Um, so essentially these are isomorphic. So this proof goes through, right? So if you sort of do this because we've added these constructors at hence. If you do e-auto, this simply goes through, and you can see how this goes through, right? So I'm restarting just to show you how the proof proceeds. So we do the introduction, and then so we see a plus here, right? In order to reduce a plus, the only possible rule that we can apply here is the eval plus. So we apply eval plus, and that will give us two sub goals, right? These are the two sub goals that need to be proven. The first one is if you evaluate the capital VAR, you get a result small VAR under the assumption that the valuation is itself VAR. This is a fact, right? This eval var is a fact, so that goes through. The second one is again a plus, so you apply eval plus, and here you're saying if you evaluate this constant expression with the constant 8, then you get the natural number 8 as a result, and that's a fact as well. That fact is the eval const fact. So we appeal to that, that goes through, and the final one is again a var. So that's fine. I mean, all we've done is we've said we proved that evaluating this program under this variable assignment gives you the this natural number result. This is fine, right? This is we could have done this just by using a functional definition by just computing, right? I just compute, write a recursive interpreter and compute it. But what we want to instead actually do is given a natural number as a result, something that looks like this, I want to synthesize the program that will lead to this, right? That's the whole advantage of describing this in this logical way. And unfortunately, this particular encoding, right, which just has these three rules, are a little bit unwieldy for actually doing interesting programs. Firstly, in order to apply this particular rule, eval plus, right, the term that you're applying this on has to precisely unify with this term. In particular, it has to have two terms n1 and n2, right? If you don't have a plus, if you just have number 7 or something else, then this term cannot be applied because the unification does not go through. You need to, because of the way the unification works, we need to exactly match it with syntax. It's a bit unwieldy, right? So If I say have an 8 here and I can split it into 4 plus 4 and the rest of the things will just go through. I don't have a way of doing it directly, but you can extend the facilities. If you take these as axioms, right, you can derive based on these axioms further facts that you can use as part of the synthesis. So here is one. Yeah, here is an example where it gets stuck, for example, right? So observe that I don't have any multiplication that appears anywhere here, right? So the term here includes a multiplication, so it won't perfectly unify with any of the three constructors, the two facts in the rule. So if you do E auto, you get stuck. Why do you get stuck? You can do intros, and then you can do plus, right? Because there is a plus here, and multiplication binds. I mean, has higher precedence over plus. This is this. There are two terms here, so you can apply eval plus, and now observe that we are essentially stuck. We sort of um, split it into the wrong form essentially. So now I need to prove that if you evaluate this VAR program, right, command under var, you have to prove 2 times var. This is not correct. And the reason why this is not correct is if you look at the other side, it says um, 8 plus var is 8, right? So really there is a var here which should appear on this side, right? It should be 8 plus var on this side. So we cannot directly do this with the three facts, with the three rules that we have here, the two facts and the rule that we have here. But we can add a helper rule, right? So consider eval plus, right? Eval plus is its constructor, right? So you can read this as a prologue rule. And if you read it, it says that in order to show that eval var plus E1, E2, N1 plus N2 holes, you have to show these um, two subgoals, right? And all I've done in eval plus prime is that I've decomposed that into one more step. So I've said that instead of the term here being just a addition, I've made it an arbitrary natural number, right? I said eval plus eval var plus E1, E2, N. And what do I expect about the N? N has to be the addition of some natural numbers N1 plus N2, and the two subgoals remain the same. So let me bring it down so that it is easier to read, right? So just compare these, right? So the first two are the same, right? And all I've done is I've just lifted this out so that it can pattern match with any natural number, rather than just the pattern, which is this plus, right? So one way to think about this is we are extending the evaluator with more rules. And because we have this as a theorem starting from the base axioms, we have to actually prove that this holds, right? Proof itself is not difficult. So um, so you simplify, you do the substitution. So substitution substitutes n1 plus n2 for n here, right? And then this is a direct application of the set of constructors. So because we've already added the constructors as a hint to the database, auto makes it go through. Okay, so now we've defined a new rule. I want to also say, consider this rule as a possible proof step in order to search for patterns. So I'm going to use hint resolve. We've seen hint resolve before, right? And I'm going to say, whenever you see this pattern, you can apply eval plus so that you continue the search with proving these three subgoals, right? So I've done that. And the other thing that we have to sort of look here is that there is a multiplication here, right? And we know that we have ring tactic, which can discharge proofs about additions and multiplications, right? And equalities, not inequalities, but equalities. So the other thing that we are going to prime auto with is we're going to say whenever you find an equality, right? This is in a section, special section called use ring, because I'm going to say whenever you find an equality, just use the ring tactic to make the equality go through. I mean, obviously, this is not true everywhere, right? It's only true for this particular example that we are dealing with. In particular, if you get a term like this, it will make that proof go through with the ring tactic. Uh, I am using extern for doing this. I'm saying that whenever you find underscore equals underscore pattern, you try to do the ring tactic. Okay, so that is in the section ring. And now what can you do? Again, the same example as before, right? So you have var plus 8 plus var, and I want to prove that that is the same as 2 times var plus 8, right? So this now goes through with E auto. And why does it go through? Firstly, because we've added eval plus prime, right? Where we said I don't consider what this number is. It's any natural number. I know this is a natural number type, so that goes through. So if you E apply this one, um, we are doing E application because we need to decompose this into two other natural numbers, right? I can pattern match any natural number, but it has to be a decomposition, a sum of two other natural numbers. So that is why we get the third goal that looks like this, right? And and now we have it in the right structure. So we have a unification variable here, and we know there is a fact which can satisfy this with n1 being unified with var, the natural number small var. So that is what happens here. So observe that when I apply eval var here, this n1 changes to var, right? That has changed to var. That goal has been discharged. And now this is a plus, right? So do a plus. It again splits into n1 and n2. We are sort of reusing the same variable. That is why n2 becomes n1 and n1 plus n2 here. Again, this is also a fact, and we know what n1 is. N1 is going to be 8. So we are going to get 8 here when we apply this rule. Yes, we got the 8. And this is again var. Okay, finally, what we end up with is this equality that we have to show, right? Which is the equality that was introduced at this point. And because we've resolved all of the variables, all we have uh, is a arithmetic expression that includes additions and multiplications and equality. And ring tactic makes it go through. And because we've added this as an extern, um, externally we call the ring tactic, and that goes through. I mean, the way I've arrived at this one is just copying the output of info e auto, right? So yeah, so again, all I've done is I've just um, evaluated this one and showed that the result is the natural number. Okay, so we have so far this can still be done with the recursive definition. Now we want to take advantage of the logic programming flexibility for searching a program, the arithmetic expression that always evaluates to a particular symbolic value, right? So this is a symbolic value. This is not any natural number, right? So this is 2 times var plus 8 holds for any variable. And I'm asking what is the program? I might ask what is the program that can give 2 times var plus 8 in the language that we have defined, in the very small language that we have defined, right? So here is how we do it. So here is the first example. So um, there exists an E, right? I'm asking what is that E, which for all variables, right? If you evaluate E under the valuation where var is the variable, the result is var plus 7, right? So this is a natural number. This is a symbolic term which evaluates to a natural number. And the question that I'm asking is what is a program which when evaluated gives me var plus 7. Of course, there are many programs. We are going to find one, right? So this is so if you do e auto, the proof goes through, and what we need to do is to actually print the proof to see what the program has been synthesized, right? The program that's been synthesized is plus var plus 7, right? And of course, you can also think of other programs, right? Var plus 6 plus 1 and so on. But here is one program that satisfies the constraint. And similarly, yeah, you can, because of how we've done this ring tactic and eval plus um, sub rule, right? Derived rule. We can also do more interesting examples. So I'll just move it to the next line just so that it is clear. So what is the program that gives the result 2 times var plus 8? So evaluate it and then print it. So the program is um, it derives a simple program, right? It says var plus var plus 8 is the program that gives the same result as 2 times var plus 8. And similarly, one last example. So what is the program that gives 3 times var plus 42? And if you print it, it's giving um, so it's basically saying var plus var plus 42. I mean, this seems very relatively simple, right? All we are doing is that anytime you want to multiply things by constant, you can do a linear decomposition, and that is what we are doing. But the key takeaway here is that we are synthesizing programs that satisfy a symbolic term, right? That deals a natural number. So that's the key takeaway. Of course, the lectures materials includes more examples and further uses, but I'm going to stop here because I think the further uses are more high-level examples, which perhaps are not necessary for getting the point across. Yeah, I encourage you to have a look at the rest of the file. So yeah, I usually name these files as um, some lecture under some topic underscore lecture for the thing that I'm actually teaching, and there is some topic.v, right? And those contain more text and might contain other material, extra material. And my expectation is that you don't need to read the extra material. Yeah, if you want, you can have a look, right? But I'm not going to expect you to read the extra material. That doesn't mean that you shouldn't, right? Just saying that I wouldn't expect you to have a look at it. Anyway, so that's logic programming. So logic programming offers a very interesting way of doing backwards reasoning, and that is quite useful for automation in COP. And that's the high-level takeaway here. And we will tend to use this without naming it as logic programming over and over again in the rest of the lectures, right? And this is sort of a setup lecture for that. Any questions on this one? Okay, so if there are no questions, let me move on to the next topic that I want you to, well, that we will have a look at. This has to be spring 2021. Yeah, so the next topic that we are going to look at is transition systems, state transition systems, and then formally reasoning about state transition systems. So this is sort of again a topic which may seem to not fit the program verification piece quite nicely. And the whole point is this, right? So if you sort of, oops, let me zoom at 100%. Can you read this? I think if I make it full screen, I can't see the rest of things. Can you see this? Anyone?
Yes, sir.
Okay, fine. Okay, so what is the point of reading transition systems? So if you look at what we had done in the interpreters lecture, right? We had a very small command language where we had this looping construct called repeat, and that looping construct repeat was designed in a very particular way. It was not the language was not Turing complete, right? So the repeat was known to always terminate. It was it took a arithmetic expression as the condition, right? And it only looped so many times, so that we can give an interpretation which basically can be expressed as self-application up to n times, right? But if you think about real programming languages, we have loops. We have arbitrary loops um, with conditions, arbitrary conditions, right? And here is a simple factorial function that you might write in a imperative programming language. You say a is 1, and as long as n is greater than 0, you do a times n. A is a times n is n minus 1. You keep doing this and return the a. That returns the factorial, right? So the problem with reasoning about this program in say Coq using the interpreter technique is that you cannot write the semantics for while this way, right? Because the while itself is on some boolean, right? Which is again a command which is looking up the valuation, right? And then it's applying some logical operator. So we cannot guarantee that this particular program will actually terminate. This is basically the problem with um, yeah, the halting problem, right? How do we know that this program actually terminates? We don't know. We can't say. But we do want to. That doesn't mean that we cannot reason about these programs. We have to reason about them differently, right? Um, so, so in the next lecture, we will actually see how to describe the language and reason about it. And the core um, technique that we use to reason about these sort of systems is to describe them as state transition systems, essentially. So you sort of convert the program model here, right? In your mind, we are building state transition systems when we are looking at this. We don't say it explicitly, right? We have this notion of what the state is in the program. And when we execute every statement, you go from that state to the next state. And we have a notion of when the state transition system actually terminates, right? And we can then build some intuition about what is the initial state and what is the final state. And we can relate how, given some initial state, what the value of the final state will be, right? And and that is what we will build up in this lecture, and that we will use a state transition system, right? And here is the factorial function expressed as a state transition system. Um, it might look a bit more complicated than what you would expect for factorial, but bear with me. We will sort of go through it, and the patterns will follow. Okay. So what is a state transition system? A state transition system has a state and a transition function, right? Which says how to go from one state to the other state. So um, our states are going to be described as inductive data types, right? Because that is what we have and that is what we will use. So there are two constructors for the states. First is the final state. The answer is some natural number, right? That's the final state in the state transition system. And all other states are going to be called with accumulator. And it has two parameters. The nn just means that both parameters are natural numbers. It does not mean that they are the same. It simply means that they're both natural numbers, right? And what else do you have for a state transition system? We will use this f for a state transition system. And when I write f0, I indicate that that's the initial state. The initial state for the state transition system, the idea is that the first is the second is the accumulator value, and the first is the n that you are supplying for computing the factorial. If I want to compute the factorial of n0, I will start with the state, which is with accumulator n01, right? And the final state, f omega, is going to be, the answer is some a, right? A is an answer. And now we have defined the initial and the final states. We have to define how the program steps through, right? And the step relation is written down as inference rules. The way to read this again, I think we've sort of seen this in 3100 previously, how to read these inference rules. Basically, the idea is that you have some um, like high assumptions and um, you have antecedents, right? And you have a consequent here. So that's the way you should read it. And here, there are no antecedents. So you just have a consequent. Inference rules are a nice way to write down formal systems um, very in a succinct manner. So we tend to overuse it in PL, but that's for a reason. When you see an inference rule, you know what is the expectation. And the rule here says that uh, if you have a state where you have n is 0 and the accumulator value is a, then you just go to the answer is a, right? And there is no transition from answer is a, and hence answer is a is tagged as the final state here, right? These are things that we are building in, right? So of course there is no safety guarantee, so you can describe whatever you want here. We in our mind say that when you transfer from with accumulator to answer is a, you're done. In all other cases, right, if you are in a state where you have n plus 1 and a, you can take a step in the transition system where the next state will be n and accumulated times n plus 1. I mean, this is what happens in factorial, right? At every step, you multiply that by 1, n, and you do n equals n minus 1. And that is what we are doing here. So if you have an n plus 1 a, you decrease n, and then you multiply the accumulator with the current number, which is n plus 1. Okay, so this describes the entire transition system. At the end of the day, what we are going to do is we are going to somehow relate so this is sort of the transition system version of factorial. And what we are going to do in the first part of the lecture is to actually relate this definition that we have in the transition system version to the usual factorial definition, which is this recursive function that we write. And the point of doing that is, of course, it is possible to directly reason about this recursive definition here. But in programs where you have more complicated languages, which might be Turing complete, you can still use a transition system to reason about the final states, right? That is what we are going to build up to in the initial part of the lecture. So we can define a transition system as a triple, right? With a set of states, a distinguished set of states S0, right? S0 is a subset of S, which are all the initial states. And then we have this rule, this arrow, which is the transition relation that relates two states, right? And if you are in one of the states, you can always move to the next state with this transition relation. So we call this a transition system. So let's see how we encode this in Coq, right? So
Sir,
yeah,
there is a definition of the factorial, but we can see that n is equal to n minus 1.
yeah.
Uh, in a recursive function, we say that we have found some decreasing function. So
Yeah.
why we are not using the same thing here? Means why
So
we are doing
the
this split transition?
yeah, so the idea is that um, the thing to yeah, okay, good question. So the thing to actually observe is this construct, right? This while construct. So recall that when we actually implemented a command language, we had the same thing, right? We had variables, we had multiplication, subtraction, and so on. But the abstraction that we had here was repeat. We said repeat this loop n times. But in this language, which is what we might write in real programming languages, we have while loop. And while loop says it takes a condition and loops so many times, right? If I modify this program to just say while n not equal to 0, right? Or say something very stupid. While n is equal to n, right? While n is equal to n, keep doing this. right? That particular function, if you think about, say, writing this function in C or something, it would not terminate, right? Because n is always equal to n, so it wouldn't terminate. So the point is, you wouldn't be able to give a semantics for such a programming language, right? Such a language as a recursive function definition. And we cannot, I mean, if you look at how we've reasoned about interpreters, in the interpreters lecture, we defined the language, we gave the interpreter as a recursive function, and we proved some properties on it. The point is, you cannot do that anymore. If you wanted to have a language with which is Turing complete, essentially, and that's the difference here. And the step towards reasoning about these languages is the transition system. And in this lecture, we are going to sort of read only about transition system. And in the next lecture, we are going to relate how we can use the transition system for those languages. Does that answer your question, Deepali?
Yes, sir.
Okay. Okay, so yeah, so we are only going to study transition systems here. Okay, so and we are still in this Frap library. Yeah, so I'm going to set all of the implicit arguments to be implicit so that I don't have to explicitly pass them. So just for, I'm going to finally relate this transition system to this factorial function. So this seems silly, but the whole point is to teach you about transition systems. So here is the transition, the recursive function definition of a factorial in its natural form, right? Factorial of 0 is 1. Factorial of n plus 1 is factorial of n times n plus 1. Right? So that's factorial. So that's factorial. So now we are going to see how we are going to express the transition system. So the first thing we had is the set of states, right? We have answer is and with accumulator. So we have an inductive, which is a factorial state, which has two constructors. Answer is, which is has an answer, which is a natural number, and with accumulator is a state which has an input and an accumulator, right? Um, and we define an initial state. Let me move it here. Yeah, we define an initial state. This initial state is what we have here, right? And the way we define it is we define it as a parameterized inductive type. This is the same as how we've done the evaluator here. So this evaluator is parameterized or indexed by this variable, right? And it sort of, for that particular variable, it relates the expression to a natural number result. And similarly, we define the initial state, right, as a relation. So it's sort of a relational view of things, where you say fact init describes a family of initial states. And what is the family of initial states indexed by? It is indexed by the input, which is the natural number. So, so this is not just one state, right? The initial state is not just one state, because n could be any arbitrary n. But I'm going to sort of fix this n for a particular transition system, because I'm going to relate the final state, this answer A, to the input. So I'm sort of fixing this here. I'm saying that the initial state, fact init, given an original input, right, it is going to sort of describe a unary relation, which is also a set, right, a set of states. And how is the set described? We have because we are describing this as an inductive type, it's a relation, right? And the relation has a name fact init. So fact init, given the original input, is the accumulator with the same original input and 1, right? So which is what we have here, with the accumulator with the original input n0 and 1. And that's how we define a set of initial states, right? It's a set because it's defining, yeah. So here we have exactly one input state for every original input. So we have set of natural numbers, so it defines a set of initial states. Okay. Any questions on this one? So we are going to see more and more of these style of inductive relations. So it's even though we are defining data types, it's better to see them as relations, right? This is a unary relation. So unary relation takes a single element and then describes a property on it. And here we are saying that fact init is a unary relation that holds true on some set of fact states. And the set of fact states that it holds true on is all those fact states which have this particular structure, where the accumulator is 1, the original input is the original input that this fact init was indexed by, right? So even though we are defining inductors, think about them as relations here. And similarly for fact final, right? For fact final, all we are saying is that for all answers, fact final is a state where the answer is answer, right? So that's the definition that we have here, right? So that's done as well. And the next thing, the important thing is we want to define the transitions, right? How does the transition actually happen? These transitions are described as inductives as well. So we sort of say there are two ways to make a transition through the system. So we know what the states are. We have a fact done transition step, right? Which is so firstly, fact step relates to states, right? And yeah, so you can sort of look at this definition, right? It's a relation that is defined on two states, right? So it relates two states. And what are those two states? There is a done state. So that's the first one. It goes from with accumulator 0, 8 to answer, right? The first one is going from with accumulator 0 accumulator to answer is accumulator. The second one is um, if the state is n plus 1 accumulator, then the next step is um, where you reduce n, but accumulator becomes accumulator times n plus 1, which is what we have here. Okay, so we defined the initial state, the final state, and the transitions, right? So the thing that we actually want to do is to not just reason about a single step, right? So here we are defining a single step. What I really want to say at the end of the day is that if you start from some initial state, right, and you continue the execution, by execution, every step of the execution is taking a step through the transition system. When you reach a final state, I am going to relate the original input that you have here with the final state here. Because I'm reasoning about multiple steps, I want to define a way of defining a transitive reflexive closure. Essentially, how do I reason about not just one step, but a whole sequence of steps, right? And here is how we define a transitive reflexive closure. These are things that you would have seen in discrete math class, right? But it is the same thing that we are defining very precisely in Cork. So it's transitive and reflexive, right? And transitive reflexive closure is defined on it's an implicit type A, right? The states could be any A, and there is a relation R, which is a binary relation, right? Which relates two of these A's, and then what you get back is also a relation. That's the transitive reflexive closure of the original relation. And what does transitive reflexive closure mean? First thing is it is reflexive, right? For all states, transitive reflexive closure relates the same states, right? So that's the first one. And the second step is saying for all XYZ states, right? If X is related to Y by this relation R, and Y is related to Z by many steps, right? Then X is related to Z by many steps, right? So this is transitive reflexive closure. Actually, I had some, yeah, so this is what I wanted to show. So transitive reflexive closure, you can, in Coq we sort of don't start with nice syntax, but it becomes very succinct when we actually write it on paper. So we define transfer reflexive closure as this relation arrow star, right? It is reflexive, so it relates given a state, it relates with the same state, and um, it also relates S to S double prime, right? If it is the case that if you can take a single step from S to S prime, observe that there is no star here, so this describes a single step, and then you can take multiple steps from S prime to S double prime. Then you can take multiple steps from S to S double prime, which is what this is saying, right? Um, yeah, so that is precisely what we've captured here, right? So we've just said the same thing. So there are two rules here, similarly two rules here, and yeah, they are isomorphic. There is nothing that is different from the definition, the formal definition on the slides. Any questions on transitive reflexive closure and how we define it? There's a bunch of syntax and stuff, but I can also help you through that, right? This A is an implicit thing. There is a relation, and it also returns a relation. Yeah. Okay. So if there are no questions, we can keep continuing. So one thing that is very surprising is that these two rules, right, don't obviously tell you that um, the transfer reflexive closure of if you can go from X to Y using multiple steps and Y to Z using multiple steps, then you can go from X to Z using multiple steps, right? That's not a fact that is obviously expressed here, because the inductor step only has a single step here. And what we are saying here is that multiple steps from X to Y, multiple steps from Y to Z, then you can go from multiple steps from X to Z using this relation R. I mean, this is sort of obvious, right? We know this holds, but we have to explicitly prove it because that's not part of the definition here, and we can prove it. So the way, just to walk you through this, right? So the way we prove this is by inducting on this um, um, this inductive relation here. So TRC RXY, right, is a inductive type, right? TRC RXY, and every inductive type has a induction principle derived by Coq. So we are going to actually induct on this. And what does this mean? We are going to do case analysis on. I mean, we are going to do the base case, and we are also going to do the inductive step with the induction hypothesis given for us. So that is what we are going to do. And the way we do it, just like how we saw in the logic programming class, is that we are going to induct on the first hypothesis, right? It has 1, 2 hypothesis here. So when I say induct one, I'm actually inducting on this term here, and then I'm simplifying. So so I get actually if we go by just to induct one, so we end up with the first thing is prove that assuming TRC RXC, prove that TRC RXC, and the reason why we ended up with that is that so there is XC here, right? So I'm sort of equating X and X in the first step. It's the reflexive step. So the proof obligations for that becomes very simple, right? So simplification just makes it. So let me do simplify here. So TRC RXC here, right? And assumption makes it go through, right? So that is what we have initially. So so if you induct one and simplify, you get TRC RXC, and that's just part of the hypothesis because of the reflexive step here. So the first one is actually the proof here. That's gone. Now we are actually doing the inductive step, right? Let me format it so that it becomes easier. Okay. So now we have to show that TRC are x0 holes, right? And and how do we prove it? We have to prove it using two facts, right? First thing is we actually have to use the TRC front rule so that we can decompose that into a single step and multiple step. But we also have the rule for the induction hypothesis. So if you sort of look at what we have, right? We know x and y are related by single step, right? I can take a single step from x to y, right? And I can take multiple steps from y to z, right? And for all z0, I can take, if I can take multiple steps from z to z0, then I can take multiple steps from y to z0. So this is sort of sitting after uh, um, this step, right? So x to y is a single step, y to z is multiple step. These are part of the hypothesis. And the induction principle says that if you can take multiple steps from z to z0, then I can relate this y, right? Saying that I can take multiple steps from y to z0, right? And I also have, so this z0 is a universally quantified variable, right? And this z0 is an actual state. It is unfortunate that these two are named the same, but actually you can sort of think about this as z prime, right? Z prime, z prime, z prime here. This z0 is different. Right? And the proof obligation is asking us to prove that this TRC are x z0 holes. So firstly, what we know is that we have to take x is only related by a single step, right? So we have to get a relation where there is r xy as part of the goal so that we can apply that. And the way to do that is apply TRC front. So if you break this up, right, you will end up with r x, some existential variable. So we are going to apply this TRC front because we are going to end up with existential rules, right? So we got two sub goals because these are the two sub goals here, right? And we have Rx question mark y because that's the existential variable, and we have a hypothesis that exactly fits the goal. So if you do assumption, I don't know whether we've seen assumption. Assumption is like assumption, except that it also unifies the variables. So what will happen here is that this hole, which is curiously named as y, happens to be will be filled by this y, this concrete y, right? In all of the sub goals. So which means that this question mark y will also be replaced by a concrete y when I do a assumption, right? So that has been proved, and this has become this concrete y. Now I need to prove that I can take multiple steps from y to z0, right? And how do I prove this? I can use the induction hypothesis. The induction hypothesis says that for all z0, again, consider this as z prime, right? For all z prime, if I need to show that I can take multiple steps from y to z prime, I can show that it is enough to show that I can take multiple steps from z to z prime, right? So that's what we are going to apply here. So I'm going to apply the induction hypothesis here. So this has become the proof obligation now, and I have that as part of the hypothesis, right? And assumption makes it go through. I mean, I'm going through this painfully just so that I want you to recognize that we are just applying the rules that we have previously studied. There is nothing fancy going on except the proper application of the rules and what you have when you sort of stare at something like this, right? And the thing is, I have x to y, I have y to z, right? Single step from x to y, multiple steps from y to z, and I have an induction hypothesis, and I have this hypothesis as well. So I'm asked to prove this. How do you go about doing this? You have to sort of look at the facts that you have, right? The two facts that you obviously need to use are TRC front and induction hypothesis, which is what we are doing. I mean, this is a nice example to actually see how to approach uh, some non-trivial proofs such as this one. Questions on this? Do you have any questions? Go through this in your own time, right? And then if you have any questions, you can ask me. And we are going to use this transfer flexible closure often, so that just to make it our life easier, I'm going to define some syntax for it. Whenever I write R, this syntax here, right? That means the same as transfer flexible closure, right? So I'll just show this one program and we'll finish here. I mean, this is an example, right? And what we are saying here is that if you start with accumulator 3-1, right? That is, we know that's an initial state, but that be on the side. If you take multiple steps, right, using the fact step relation, then you end up with the answer is 6. This is not saying you go all the way. It's just saying you can, if you take enough steps, then you end up with the answer is 6, right? And how do you prove it? You have to sort of decompose this transfer flexible closure into its constituent relations, right? So there is TRC front and TRC refill. Again, our logic programming is going to come in handy, but I'm just going to do this tediously so that we see what is happening. And then let's automate this. So you apply TRC front because we know we are going to take one step and then a sequence of steps after that. So if you apply TRC front, right, you end up with two subgoals that look like these, right? First one is the relation, second one is a transfer flexible closure again. We have an existential variable here. Fact step is clearly defined, right? So fact step is clearly defined. It tells you given this state, what state you end up with, right? So simply appealing to the constructor, make it go through. So you just apply fact step, you find the candidate for y that gets substituted here. You have an arithmetic expression here which you can simplify, and you can keep doing this, right? So again, I made one step through the transition system. I want to do more. Again, you apply TRC front. So you decompose that into a single step followed by multiple steps. Again, fact step goes through, right? And you can simplify this result as well. Okay, that's also simplified. And now again, we have 1, 6. This is also one step followed by multiple steps. Apply TRC front. Apply fact step. You end up with this, right? You simplify. Again, TRC front, you have to break it up. Now we know that when we have a 0, 6, right, it's going to, the only rule that's going to apply is the fact done rule. Because fact step rule can only be applied on any natural number that is greater than 0, right? And we have a 0 here, and the only rule that can apply is fact done, right? So we are going to apply fact done. So this is going to become answer as 6. And these two are related by reflexivity, right? And we have reflexivity as part of the definition, right? TRC refill is reflexivity. And we just asked reflexivity to discharge this proof. This was exhausting but uninformative, right? We are just mechanically applying steps. This is precisely where we can automate. In this simple case, we can just automate it using repeatedly applying the E constructor. So constructor is a tactic which picks the right, the first constructor that unifies. E constructor also handles with these unification variables that are present there. So if you repeatedly apply the E constructor, we actually make the proof go through, right? So this is, we are not using auto here. We are just mechanically saying, just apply the first constructor that matches. And you keep doing this, You will just make the proof go through. So you don't have to actually do these steps. You just repeat it and you're done. Actually, I'll stop here. I think what we've done here is we've just proved a single example, right? Ultimately, I want to relate this factorial definition to the functional definition of factorial that we have defined initially, right? That is what we'll do in the next class. But yeah, we'll stop here. So E-constructor does the simplification as well. Yes, it does. Yeah, yeah. And typically, simplify is all over the place, right? So it is just a useful thing to do. When you have an expression, it is always useful to simplify. Of course, we saw examples where that didn't work in one of the earlier lectures, but mostly E-constructor just works and it does the simplification. Okay, so I'll stop here and then we can continue tomorrow. Bye bye.
Sir,
Deepali, yeah.
will you discuss the solution of the assignment for
Yeah, so there was this question of whether we want to discuss the solution. I'm happy to, but if it benefits everyone. Otherwise, um, fix the appointment with the TA, right? And see whether that helps.
I mean, only for the BST part.
Okay, that's fine. So I'll just ask on Slack whether everyone will be interested and then we can discuss. Is that okay?
Okay, sir.
Okay.
And sir,
Yeah.
I haven't missed because of the assignments. I haven't done much about that.
Yeah, that's fine. That's fine. So let's meet
Yeah. So
next week.
by the end of week, I'll do it.
Yeah, that's fine.
Yeah.
Okay. Wonderful. Talk to you later. Bye bye. Bye everyone.